Yeah, so thank you very much for the kind introduction, and thank you all for joining my talk about the visual inspection of transparent objects with light field methods. Before we go into the technical details, I'd like to give a quick motivation why it is at all interesting to cope with the inspection of transparent objects. So first of all, we are dealing with transparent objects in our everyday lives in various situations. For example, we want the windshields of our automobiles or aircrafts to provide us a clear vision, to be free from any impurities. Of course, when we build optical systems, objectives, lenses, we want them to accord to certain quality requirements. And quite interestingly, also when we think about medical applications, for example, a laser guided eye surgery, I think it gets really clear that we want this lens to be free from any air bubbles, for example, that could redirect the high energy laser to the wrong position in our face, because we only want to get our vision improved and not to get our freckles removed, for example. So when speaking about these applications, it gets quite clear that we need to have some quality control. And one possibility to do that is to employ human inspectors. And what human inspectors typically do when they inspect a transparent object, like this glass gob, for example, which is a kind of a pre-form that is later on used to build lenses out of it, for example, they illuminate it with a very bright light source from the side, and then they rotate it around and look at it from different angles. Like, for example, here, from this perspective, you might see a little bit of dust on the surface, but not any severe defect. Then you might rotate it a little bit further. Still, you don't see any defect, but very strong reflections from this bright light source. And eventually, we arrive at the rotation of this very object, where you can then make out this tiny air bubble that is hidden inside the object. So what a human inspector does when inspecting transparent objects, he acquires a light field from the object by looking at it from different perspectives. So the main idea of a light field is that you have the directional information of the light inside this data. And the problem with doing human inspection is that it is very fatiguing. You have subjective results, and you might oversee defects, what could be very crucial depending on the application. So what can we do to automate this process? For simple types of objects, like such a transparent object with a very simple geometry, there are elaborated methods on the market. For example, we at Fraunhofer IOSB, we often employ this so-called purity principle, where we couple different illumination modalities. For example, this bright field illumination in red, illuminate the object out of the perspective from our camera. We use a retroreflector behind the object so that the light gets directed back into the same optical path. We can inspect the transparency profile of the object by that means. And to find scattering particles, we illuminate the object from the side with the assumption that in the case of no defect present, no light reaches the camera, and if we have something scattering like this air bubble here, some light will be scattered into the camera and we can make this defect visible. For such simple objects, the problem is already solved. You can buy existing solutions. Now, if you look at objects with a more complex geometry, like this double convex lens here, for example, you can still use the bright field setup as described before, because the retroreflector will mitigate all the optical effects of your test object. I mean, this lens will of course redirect the illuminating ray, but the retroreflector will direct it back in the same optical path, so the refraction will be mitigated. Also, the dark field works to some extent, but you will additionally get disturbing reflections from the surface of the object in your camera image, and it will be hard to distinguish them from the real defects. So this was the goal that we wanted to achieve with our light field philosophy. And the idea now was to introduce the concept of light fields into all the main components of an inspection system: illumination, image acquisition, and also the image processing component. And here I'd like to show you in this talk a novel sensing device that we developed at Fraunhofer IOSB. We call it the laser deflection scanner. And this thing consists of two components. We have on the left-hand side an emitter, and it illuminates the measurement field with parallel laser rays in a time sequential manner. So only one ray at a time, and we scan through the measurement field. And on the receiving side, we basically have a large lens or a large parabolic mirror, and in its focal plane, we place a two-dimensional detector array. And now this kind of optical setup transforms directional information into spatial information in the following way. Consider a ray that goes through the measurement field without any deflection. Then it will always be directed to the center of our detector. You can imagine it the other way around would be that you place a point light source in the focal plane of a lens, and then you would get a collimated light beam. And what we would sense here, we call those structures deflection maps. You can see them at the top here, is the two-dimensional distribution of deflection angles that we get for this one measurement position. Now, for example, if at the position M2 in the measurement field, our ray gets deflected by an angle alpha, it will hit the detector with a spatial displacement that corresponds to this deflection angle alpha, and our deflection map would look something like this. So no matter where in the measurement field we have a deflection by this angle alpha, we would always get such an intensity distribution on our sensor. So this setup basically, that the receiver, it loses all spatial information. It just has angular information. But since we scan the measurement field time sequentially, we regain our spatial information. So we know for each spatial position the two-dimensional deflection distribution. So how does this help us now for our visual inspection task? Consider that we have such a planar convex lens, and we have the red circle should be a tiny air bubble enclosed in the object, and below there we have a large surface defect. And now let's just hypothetically scan through this object. For the first ray here, we would have a small deflection, because that is what our object is supposed to do. And now a one-dimensional section through the deflection map would look like this image above on the right-hand side. We would have a peak that corresponds to this deflection angle that we have at this position. If we scan further along this, the object, the deflection gets smaller, so the peak moves towards the center. And if we eventually hit a scattering material defect that scatters the light into multiple directions, we will have a very broad deflection profile, because we have multiple deflection directions present behind our object. Afterwards, we have a defect-free position, so the peak just continues to move. If we have a strong surface defect, we might get a strong repositioning of our peak away from its intended position. And finally, we have a defect-free position again. So the idea now is to acquire those deflection spectra for our complete test object, and to find discontinuities between adjacent deflection spectra. That we want to find positions where we suddenly go from a peak to this broad deflection spectra, or where our peak is suddenly moved to a completely different position. And to detect those defects, we also need now to introduce this light field concept in the processing component of our imaging system. So the typical thing that you would do if you want to find spatial discontinuities in an image is that you calculate or approximate a kind of gradient on your image. For gray level images, we all know that we calculate edge images using a Sobel filter in the easiest case. But what do we now do for this kind of image, where in every pixel we don't have a single value or an RGB value, we have a two-dimensional deflection distribution in every pixel? What we did is to start with the symmetric different quotient. So illustrated here, if we want to calculate the gradient for this center deflection spectra, then we just take its horizontal neighbors, put them in a suitable distance function, and for the vertical component of our gradient, We take the vertical neighbors and also put them in this distance function. Afterwards, we can, for example, calculate a norm on this gradient. Then we have a scalar valued image again, and we can continue with all the traditional image processing, machine learning, and so on. We did a lot of research concerning finding suitable distance functions for this purpose. The Earth mover's distance can be used, but we found that the so-called generalized Kramer von Mises distance works the best way here. It's a bit of complicated to compute it, but we also derived a fast algorithm so that you can use it in real-time applications. I'd like to show you some results we obtained for 2 experiments. In the first one, we wanted to inspect these plastic covers of our car headlamps for defects. It's a very large and complicated object, as you can see. And at the top, you see the conventional bright field image that you would get for such an object. And on the bottom, in pseudo colors, you can see the result with our proposed approach. And you already see in this image that there is a lot more going on here in the test object that is not visualized in the conventional way. And even if we look at the magnified regions, we can see that we can make a lot more defects visible with this light field approach, and also the contrast to noise ratio supports those findings quantitatively. Another very complex object that you might all know is this bullseye that we all have in our washing machines. It's very complexly shaped and transparent, and here it's especially interesting to have no open surface defects towards the inside of the washing chamber, because that could damage your laundry while washing. And also here, when comparing the 2 images that we obtain, you see we can make a lot more visible with the light field approach. And here, for example, for this second defect region, in the bright field, you can only see the marking from the customer where he marked the defect, but the defect is not visible, and it is clearly visualized with the light field approach. So those was our work regarding light field acquisition and processing. And now I'd like to show you 2 last slides for our approaches concerning light field illumination. You might have seen our experiment at the control fair, for example. What we try to do here is to kind of inverse the light transport, and we have a method to determine light field illumination recipes that are specifically tailored for the object that you want to inspect. And here we have, this is part of a plano-convex lens, and you can see that there's some surface defect on the top right corner of our lens. In the bright field setup, you can make it out, but it's quite hard. You need to do some further image processing. And when you look at the image that we obtain with the tailored light field illumination, everything where light can transmit without redirection through our object is colored in red, and any deviations from that direction are colored in blue. So we developed one light source that combines a bright field illumination in red and dark field illumination in blue in a common light source. And this is just the bare RGB camera image, and you basically would have to count blue pixels to determine if there is a defect or not. So here we shifted a lot of the work into the illumination component. And that already brings me to the conclusion. I hope I could give you a short insight and motivate that it is quite sensible to use light field concepts for visually inspecting transparent objects, and not only in one component, but in all of our inspection system. And yeah, if you have further questions or ideas to collaborate on something, feel free to approach me after the talk. Thank you.
Hey guys, welcome. This talk will be much more applied than the talk before, since we are using computer vision for our manufacturing processes. And one of these technologies I will present to you in a project we do right now in collaboration with several partners. One of them is Profactor, where Dr. Eitzinger will have a talk tomorrow here. And what we do at our institute, we build airplane parts. We try to automate the manufacturing processes for fiber reinforcement parts. Since it's an additive process, we stack layers of fabrics, in our case carbon fibers, in other cases glass fibers or other materials. And one of the first process steps in that process chain is the preforming, where you drape the fabrics from the two-dimensional state into the three-dimensional state, how it should be done in your mold. This is done usually manual. We tried several approaches to automate this process, and right now here we try to focus on the mix between automation and the manual process. So we will try to help the worker in his process, the draping, by delivering him materials, assisting him. Here you can see of our research right now a picture where two robots hold such a cut piece that the worker can do the draping and doesn't have to focus on the rest of it. We do this also by simply using one robot and the worker, and together they transport the materials. And here you see the use cases we have. For us, it's a frame of the aircraft, which is the circumferential reinforcement. We also have a maritime use case, which is a propeller for a boat, and also a very fancy sports car, the Dallara Stradale. And there were a lot of discussions on how we do the process, how do the robots execute their movements, or how is the quality assurance done, how is the draping and fixation, but there were never a question on how we pick up these plies from wherever they get delivered, since where you pick the plies defines where you place them, since they don't change the location on the gripper during manipulation. So we introduced a new system, which we already developed at the German Aerospace Center. It's a rather standard industrial camera with some polarization filters on them, a red flash that's good for reflections of the carbon fibers. And you see in the corners of this image here these markers. They are calibrated to the robot and to the camera, and then we detect the cut pieces by a rotation and template matching where they lie on the table, and then the robot also knows where this ply is lying due to these markers. Here you can see one of these applications where we grip some plies, deform them, and directly place them in the three-dimensional tool without ever touching them by hand. And everything is done by machines, which is good for repeatability and good for the material, because they are very fragile, and if you touch them by hand, you really destroy them really fast. So this already works really nice, but this is focused on dry carbon fibers. We needed to adapt the system to be useful for the Drapot project. This whole system was encapsulated software with a manufacturing execution system where everything is planned and organized. We used the camera mounted on the robot, and also we used a flash. But in this human-machine interaction scenario, there may be difficulties with this setup. And therefore we needed to change some stuff, which is we need to modularize the software that we only can use the computer vision part of it, implement some stuff we need for our scenario, mainly MQTT, and which I will explain later why we did that. We needed to use a color camera. So far we only used monochrome cameras, now we needed a color camera. Also using ambient light and camera calibration with stationary cameras that are not mounted on the robot. Yeah, our software was coded in C++. The whole framework was changed to a more object-oriented approach, which it then made it really simple to make a Python wrapper around this C++ code and extract the camera handling and the computer vision calculations, as well as the coordinate calculations. And in the end, we could use a simple Python MQTT library to implement this into our existing system. And here you can see the first result of that, where we also implemented several camera calibrations. Since we have small patches, they get delivered by an automated guided vehicle. And also we have long patches, 4.5 meters long, which are lying on a long table, and we need to switch on the fly the configurations about that. And then this system automatically gets triggered and calculates these positions. So this was done for our old system, but for the new system we needed to use a color camera. And here you can see why. Since the other use cases are using other materials like pre-preg, where resin is already in the fabric. They are delivered with protection films on top and beneath it, and they have color changes by every batch, and you don't know which color it will be. For the propeller, we had carbon fibers and glass fibers. Glass fibers we never used before, but you can already see down there that the background is not quite different from the fabrics themselves. This was then solved by looking at each color space individually and doing contrast enhancement for the respective color that was found in the image. And there, the fabric itself could be separated quite good from the background, and also the coordinate calculation could be done very easy with this setup. And why do we need a stationary camera? Here you can see the end effector that is used in the project partner's robot cell. This thing is quite huge. There's a lot of media going to the robot, to the end effector. There was simply no space left to put the camera on the robot. Therefore, we needed to put the camera higher above the table, that you don't have collision with the robot. You can get anywhere. And also, if you higher the camera, you need a much stronger flash, since the distance is changing. And therefore, we wouldn't use a flash, since there's a worker in the robot cell, and we won't expose the worker to this high energy flash we need to get a quality image. And therefore, we can only use with ambient lighting. And also then we need a perspective transformation, since we can't put the camera in this height directly perpendicular to the table. When using a robot, it's really easy. You can change the position of the robot to be directly perpendicular to the surface. So perspective transformation was done, and you can see in the image directly that these red squares, they are the same, and with the transformation the final image is quite good calibrated and rectified. And this is needed for our cut piece localization, since we use pattern matching, and the pattern is in 2D, and to have the same sizes we need perpendicular to the cut piece to have the same area we are looking for. And then we tried it out, and we detected several materials, and you can already see here that the ply isn't very uniform. It has like cutouts to measure fiber angles on the cut piece. It's wrinkly, it's reflecting heavily, but with the contrast enhancements we could do with the color camera, it was really easy to now also detect like these parts. And how this is looking then during the process, here you can see how one worker is transporting the fabric from the table where it was gripped to the mold. And here it's especially important to grip it correctly, since the pre-preg is already sticky, and as soon as you touch the surface the first time, it's placed. You can't change it really. So the first lamination point needs to be really precise, and that's what we could establish really nice with the system, because we continually grab the cut piece on the correct position. So to sum this up, like told, this was a much more applied talk about computer vision, but without the system it would be really difficult to handle these materials in a precise way. The pre-pregs aren't that difficult to handle because you can touch them with the protective films on, but the dry carbon fibers and glass fibers, if you touch them after they have been cut, they lose fibers all over the place, and you have to be really careful with transporting them. So getting rid of fragile pre-draping parts on the table to grip it, we now can simply use the computer vision to detect the cut piece, send these coordinates into the system, and then the underneath lying manufacturing execution system tells the robot to grip it and to place it together with the worker in the mold. And also this approach now with like helping the worker in his task is much more sufficient than automating this process completely, since humans have rather nice tools in terms of hands. They can do things very precisely, and they have a really nice and fast feedback, which robots usually don't have. So you can take advantage of the workers in his task he learned over years in the draping, and simply let the robot do the stupid tasks by delivering like 4-meter long cut pieces, which would be really difficult for one human alone, and stuff like that. And yeah, if you have any questions about this system, please ask me, and I will guide you to the expert on computer vision, which is my boss, Alphonse. he developed this whole system. I'm more on the applied side of this. I know everything about the rest of the process. So if you have any questions about this technology, just contact me and I will forward you to my colleagues. So if you have questions now, please feel free.
Thanks for the introduction. Yeah, then we can start right now with the topic. So at first, why do we need synthetic data? So we will start with the first introduction of general optic quality control. As you all know, optical quality control helps us very much to automate processes. Let's have a look. So perhaps it's better from this side. So optical quality control helps us to automate processes, to reduce human effort, and give us documentary content to show what has been inspected and controlled. And deep learning is one way of implementing such optical control for automatic evaluation. Deep learning depends on, at least if we use supervised methods, on a large amount of data. And to generate this data or to achieve this data with real-world data is quite cost-intensive. You need a lot of human labor effort, you need perhaps a lot of energy costs, as we will see in the example we will have in this speech when it goes about welding seams, which are, as for sure, cost a lot of energy to produce these welding seams. And if you want to have a deep learning approach, then you need also a lot of scrap, because you don't, to have only okay parts will not be sufficient for a deep learning supervised approach. So all in all, we have a lack of data. And to compensate this lack of data, we can use synthetic data generation as approach to compensate this lack of data. So there are different ways of doing this. One is model-based software simulation, computer graphics way of doing it. For example, as you see it in this traffic scene by NVIDIA, or for logistic approaches, or from our institute, from Fraunhofer IPA, in this left corner, where we have a 3D model which will be adapted, and using rendering tools we see different kind of scratches. So this can be used for quality control. Let's say the other ones, like this traffic scenes or this logistic image, looks nice but is perhaps not realistic enough. So we have to make a big difference between realistic images and nice to look at images. Nice to look at images are produced quite easily these days, but images which are giving us pictures which looks very similar, like the one we would get out of the camera, is quite difficult to achieve, or more difficult to achieve. And that's exactly where we like to point our solution out. But at first, in contrast to this simulation-based way of doing it, there are also, as you all know, generative approaches. Generative AI is, I think, one of the biggest topic these days, one of the biggest growing technologies, as you are all aware, with DALL-E or for sure ChatGPT. And you see here, for example, a lot of human or human-like pictures, but none of these persons really exist, as you perhaps have already seen on quite other homepages or in the media. So these generative approaches can be used to generate new data, as we know. As you all know from DALL-E, you can use text as input to generate different kind of images, like an astronaut riding a horse. But this is perhaps not ideal for the field of quality control. To describe defects like cracks or bumps or whatever by text, and also the localization is quite difficult and a lot of effort. Perhaps it's more useful to use semantic masks like we see here. So we have here the original images, we have here a semantic mask which is already adapted, and this semantic mask is then used to produce the synthetic image. And so it's much more intuitive, much more easy to use than when we use just text as input for our image generation. The main example I would like to show in this speech is the control of weld seams, because it's a very good example, because as it's obvious that it costs a lot of energy if you use arc welding, or if you use lasers to produce these welding seams. It costs energy, it costs material, so you have a lot of cost aspects in taking into account. So let's start with the amount of images we had in the beginning. So we had here 202, I think perhaps it's on the next slide, more representatives. So we have 202 images acquired, which is when we use what's quite common for evaluation and to recognize if we have overfitting or any kind of misleading data leakage problem, to separate the data sets in different folds. And then if we take a look at the different kind of folds, we see that we have for the two kind of defects which we are focusing on in the also published paper and in this presentation, is quite underrepresented. So we have for the first fold in this welding spatters only 19 examples, which is far too less to get a reliable supervised learning model trained. And for porosities it's even worse, because we have here only 9 examples of these kind of defects, as we have not only to split it up in the folds, we have also to split it up, as you all know, for training data, validation data, and test data. So now you see, sorry for that. Now you see already how these images can be generated. We have on the left side the original image, on the middle side we have the semantic mask, which is now adapted, and you see how it is rendered in the real time. So we have not speeded up this image, this video. It's really the time which is needed for generating the image. And it's not just a copy-paste, it's really that these defects are fitting to the environment. So it's try to produce the model we have trained, the pictures as like they would be produced in the real world with the real camera system we have set up. So, but we don't do this just to have synthetic data. The main aim is that we get a better supervised learning model, a better quality control in the end. So now we have to check if we have really a benefit out of these added synthetic data. For measuring this, we use the intersection over union, or the mean intersection over union. As you see in this upper left corner, the intersection over union is defined with this graphic, let's say. So we have, let's say, this is the position, the ground truth. Here we would expect the data, the bounding box for it, and the other rectangle is the area where the model has said the defect is. And then we take a look at the intersection of these two rectangles, put this in the nominator, I think it's the English word, and the sum of these areas in the divided by the sum of these areas. So this is intersection over union, and we use this as measure. The more the two rectangles, the ground truth and the detected area fits together, the more they lie in the same position, the better we have localized all the defect. And then if we take a look at the intersection of a union, how does this change? If we just use the real data, we have only an intersection of a union of 9.67 for the welding spatter and 0.033 for the porosity, which is for sure useless. You can't rely on this good enough to use it for any kind of quality control. But if we step by step increase the amount of synthetic data up to 100% additional synthetic data, so we have 202 real images plus 202 synthetic images, then we can increase this intersection of union to a value of 23.44 for the welding spatter, and for the porosity to 28.02. which then makes it useful. And to be honest, in the most cases it will not be so relevant to localize a welding sputter the exact position. But we know now we have a more or less reliable result we can use to evaluate if this welding seam is good enough or not good enough. So in this slide you just see a little bit of graphical representation. It goes from right to left by stepwise increasing the amount of synthetic data which has been used for the second model, so the model which then does the real evaluation of the welding seam. And we see that on the left side we see the ground truth, and we see step by step, if we use more synthetic data, we get step by step more to the ground truth. This is in this case for sure not a quantitative but a qualitative way of looking at the results. So all in all, synthetic data can be used to compensate the lack of data, which is the main purpose why we use the synthetic data. And by the way, the aspect is not only that we now have more training data, also we have already labeled data, because the semantic mask which is used to produce the synthetic image is, in the next step, the label, the ground truth for the training process. Yeah, as you have also seen, the experiments show significant improvements in the segmentation performance when we combine synthetic and real data. And of course, the most benefit we will have for underrepresented classes, which is very often the case for failure parts, because you don't want to have failure in your production. And you, for example, if you have a failure rate or in the ppm range, it's quite difficult to get any kind of not okay data. And so this is, I would say, a real benefit to also introduce supervised machine learning approaches also in the field where these days it's difficult to get the right amount of real data. So then I'm more or less at the end of my presentation. You can also have a look at this demonstrator which I have shown in the presentation in Hall 10 at the booth 10G45. And we can have the details discussions beside the questions you have perhaps right now. And if you want to get in touch, you can here also find my contact details. So thank you very much for your attention, and if you have any questions, I'm happy to answer.
My name is Markus Murschitz. I'm working at AIT at the Center for Vision, Automation and Control, and for me that is really important because in the topics I'm working at, the control part also takes a more prominent role than in most of the talks we have been hearing about, because it's very robotic. So what I'm talking about is automated loading and how it can help us to get over the problems we have in loading scenarios, especially if we think about the last mile problem. We know that loading is very essential as a link in the logistics chain as a whole. And we also know that there is a huge amount of labor shortages in that area. It's very hard to find people who are skilled enough to operate the machinery that's needed to process and to load stuff. At the same time, we know that if we would automate it, we would most probably be able to increase productivity and efficiency. And at the same time, we would be able to increase safety, because we can, in a lot of processes, make the human be outside of the area of danger. And at the same time, we also hope that we would just have less accidents by having an automated system. So where I'm coming from is the large-scale robotics lab. That's also the philosophy we have there is that we don't think about our working machines, such as cranes or forklifts, as machines, but we think of them as robots. And in order to think of them as robots, we have to model them accurately enough so that we can control them as if they would be robots. Meaning especially that we have to be able to model the hydraulics and the difficult parts in such a system to such an accuracy that we can treat them as robots. So we can see this is our open-air test site for autonomous machines, where we test a lot of machines. And here you can, for example, see the forklift, and we have a container and like a very nice setting here to test and run these machines and develop on them. So what's the current state of the art? If we think about the last mile, we have structured environments where this problem is more or less solved, the automated loading, especially with forklifts. These environments are optimized for logistic operations as a whole. Usually you have some kind of pre-planned routes in warehouses, and you have very trained personnel which can easily operate what is left to do there, and which are usually out of the way of the autonomous machine if necessary. And on the other hand, we have unstructured environments, most prominently I would say construction sites, where we also have loading operations going on. And we want to slowly approach these very unstructured, ever-changing environments and be able to map them, to reactively navigate within them, and to do that reliably and safe. And at the same time, we want to be able to deal with all the challenges that go hand in hand with this, especially weather conditions, light conditions, and also mechanical issues. So if we think about the harsh conditions and what that means, we can see the following things. One thing is that we have more or less weather-related things, such as it's very sunny, therefore hot, it's very rainy, or it snows, and things like this. But we also have elements that are very hard in a different way, such as reflective puddles, where even LiDAR and camera show like huge artifacts usually. And we have slippery and bumpy ground, which are mechanical effects that compromise the operation of an automated system in that area. So if we think about this, we have a lot of variety in problems we have to tackle. So what we started first was we tried to catalog them over years, first for vision, then also for LiDAR. So we have done that over many years, and we most prominently presented this as the Robust Vision Challenge. That was in cooperation with CVPR, ECCV, ICCV over many years, where we cataloged all these problems first to then be specifically able to tackle them. So if we now think about the last mile delivery, what we can see is that if we think of the system I'm going to present, then we think of a situation where we have a different situation every time. And that is very well represented by the system I'm presenting here, which is a truck-mounted forklift, which is going to be mounted at the bottom of a truck and taken with the truck and can then operate in a completely new environment, completely autonomous without any loading infrastructure other than itself. And this gives a lot of chances for delivering processes in the future. So, and what we want to do now is we want to automate these things. So what we see here is a picture of our forklift in the test area of Digitrans, where we tested it under rain conditions. And I will now introduce some of the components. We have an all-weather obstacle detection. We also continuously test new sensor technologies. In this case, for example, we have a radar system and infrared baseline. Then we, on the front side, have like a multimodal object detection system for the most important features such as pallet detection and loading platform detection. And we have in the core of this all an intelligent automation system, which is then very much in control of this high precision planning and control system that runs all the actuators of the system. So if we look at the field of views, this is what we have. We have like collision detection sensors on one side, and on the other side we have object detection sensors. And the reason for that is that the system is driving in one direction and loading in the other, which we will see soon. So here's now how we tested it under rain conditions. I mean, there are many tests like this, but this is a setup where you can regulate the amount of rain. It looks as if it would not rain very much, but if you stand there, you would feel very different. Yeah, and we found out that our system for obstacle detection, which is more or less an adaptation of a system that we have been developing for a braking system for tramways over many years, is very robust against rain as a hampering factor. far more robust than most of the other systems we tested. So, and the reason for that is that it's it has 3 cameras and has explicit inbuilt rain coping mechanisms in the stereo system itself. So in the very early steps of the stereo. Okay, now the pallet detection. Obviously, if we want to move pallets, we have to detect them. Usually we think of Euro pallets for now. What is the difficulty here? That they look very different at different age, but also in different weather conditions, if they are wet or if they are old, and all these things have a huge impact on the appearance, which made us think that we should go the direction of going more in using the geometric features as a main anchor for the detection, and that's what we did. And we did so by using only geometry-based detection features, which combine a bottom-up and a top-down approach by representing first geometric elements such as edges and corners, and then connecting them in the deep learning network itself to give a complete response for the entire entity of a palette. So it's a bit similar, the network, if anybody knows, to CenterNet from the voting mechanism, but it has a lot of other features for the edge detection, for example. And once we trained this on purely synthetic data, we could use it on real-world data quite well, and we were very surprised in the beginning, and it gave us the huge opportunity to run it again and again. Whenever we found problematic situations, we just created new synthetic data and evolved on that. And now we have a very controlled mechanism for creating this data for outdoor scenarios, also for other problems actually. At the same time, we need some intelligent automation system, and here I want to emphasize one thing, that this has to work with a human also. So we have these problems with the system that usually you sometimes want to be able to tell the system to change either something or to stop something, and in order for this to work, to have like robust fallback mechanisms also for human intervention, you need to have some kind of more or less undo mechanism in the behavior. So for example, if you load a pallet and it was the wrong pallet, you want to put it back before you take another one. And these things are very important. You don't think about this at first, but once you start to really develop a UI for these systems, you find out that this is essential for being useful. And that's also what we found out in our user studies. So that's one of the important things. I mean, there's a lot of adaptability in the behavior, especially regarding mechanical mechanisms we will see later. And we wanted to build a system that we know how it works. It was on purpose not completely AI driven, but after like a recipe, so that we know what it does and when, because we need this trustworthiness in that case. So, and obviously we needed some path planning. I'm not sure. Sorry, video does not play. Second. Yeah, doesn't matter so much. Okay, on the left side we see that for the path planning we have an approach which replans all the time. Whenever we give the system a new query, more or less, consisting of a palette to pick up in the current position, it will determine completely new paths within the environment, which is already mapped in that case. So this means that for every palette, the path is planned anew, and there's no like pre-built paths, but they are optimization based. And it's real-time capable, and we can see here already that it works together with the with our control mechanisms to then in the end pick up the pallets. And here it's I have to emphasize that this hydraulic actuation is something where you need to model the system in a detail which is not common for robotic systems, for example, which are usually driven by electronic motors and not such hydraulic mechanisms, which are far harder to model. Oops. Also, the user interface has been designed in a way that we know that it works with a human, so this has all been verified. User studies have been made, and we did continuous tests with experienced forklift drivers of different age and gender, and did like a complete evaluation. And if we now look at the results of this, we can see that there's several sensor systems, and we have this forklift with the user interface completely operating according to plan, where we select the amount of pallets we want to unload and load from A to B. And then the operation starts. So I will now switch to a more detailed view, just the inside view. And what we see here is how the planning for loading from one loading area to the other loading area happens. So all the pallets in this area will be put here in the end. And we are now able to run such scenarios with a 99.5% success rate. So we are getting there. But obviously there are always things to be done. One thing which is not very good currently is that we are not very good at snow, especially due to the change in friction, which we can't deal properly with currently. But that's the next thing we want to tackle in this winter. I want to just emphasize on one more thing here. So here we can see something which is very important for robustness, that we use the mechanical sensors also as a feedback for the system control. For example, here the forklift, its fork more or less feels where the loading platform is and then goes up and out of it. And whenever we could do things like this, they are far more robust than everything we could do with any sensor. So the tactile measurement is very accurate usually. Here we can also see how it can deal with problematic situation and self-correct. So in the behavior we already employed a lot of correction mechanisms and robustifications. Okay, so thank you very much, I think.
Thank you very much, Ilma, for the moderation, and also thank you to AET, which is all the time supporting us, and I have been several times here to do some presentations. It is very interesting and it's a very good stand here, and I'm very proud to also present some sort of an Austrian contribution to the international society. So my talk is about 3D measurement in the so-called Erdstall facilities. The first question, what is an Erdstall? I asked the same question also last year at the conference in San Francisco. Nobody checked it, because Erdstall is a very old name, which means it's a Stelle in der Erde. So this is a German expression. It's a place underground, and it's a very old expression, but it is very used in the science of archaeology. So in this case, this is an Erdstall, which is a man-made digged cave underground. As you can see here, it consists of 7 chambers, so 1 to 7, and the lowest part is about 6 meters below the ground. And all of the chambers are connected with a certain slips. So this is a small space, maybe 40 centimeters in diameter, and one has to climb to the slips either vertically or horizontally or vertically to get into the space. So in this type, this is a very special one. It's in Upper Austria. It has several features. It's a so-called type B feature of an Erdstall. We know all the other places which are for vineyards to store the wine, or there are other facilities just to get from one place to the other place. But this is a type B Erdstall. It is good to hide people. And it was erected and used 1100 to 1400 Anno Domini, means it is 800 years in age. It consists of several chambers. The total length from the beginning to the end is 37 meters, and the height deviation is 6 meters. There are building shafts, which is a construction shaft. I will tell you something about this later on. And there are niches of lamps to have some illumination. And there are benches. So this is a total construction of the Erdstall. And now I would like to introduce the metrology problematic of this Erdstall. You can measure this Erdstall in old ways, which is, you know, the several spots, number 14, number 15. You can measure it with the caliper about the distance and also the direction, so you can have some idea about the size of the Erdstall. But we want to have a total 3D geometry of all of the points of all of the Erdstall. And this can be achieved either by LiDAR sensors, so you can apply, and we also applied LiDAR sensors within the Erdstall. The first was a Leica sensor, BLK 360, or the other was a Matterport Pro 3D sensor. And with these sensors you can accurately measure the 3D geometry from a single point. So the advantages of these sensors, these are long-range sensor from 0.5 meters, maybe to 100 meters, and it is very accurate and reliable. And within this image, if you have a look to the image, you see the result of such a LiDAR image. So you see, so this is the cave underground, and you also have some structure overground. So there are the cars, there are the trees, but I have to tell you, the clouds are not true. So the clouds are man-made driven. But the other points are all single ones from the LiDAR sensors. What are the disadvantages of LiDAR sensors in this case? It takes some time. You have to place the LiDAR sensor and hide to another place, because it takes 1 to 2 minutes from the sensor that all of the sensor is capturing all of the area. And the disadvantage is also some sort of the long range, because in the cave you sometimes have places with very close distances which are closer to 0.5 meters. And thirdly, it does not get into niches. And so these are some disadvantages. What we applied here is, this is our sensor. It consists in general of a tablet. This is the center part of it, and some illumination, but it's a handheld device. So with this handheld device, we have then been able to measure all of this. How does it operate? So you can see the operation in general. It has a front end which does the odometry. It is 10 times a second. We get 3D information of one single place, because within the sensor we not only have the camera, RGB camera, but also a depth camera, and for every single pixel we get the depth information and the color information. So this is done 10 times a second. After this we get this image, this odometry data to the backend, which then operates once a second, and it takes the keyframes from one frame to the other one and combines different frames, and it tries to do a loop closure detection to get from one image to the other, because by the scanning you move the camera and you have several different images, and by this you also have some estimation of the camera position online, which is done back end once a second. After this, then you get the 3D map generation, and with this you can have the map visualization on the screen itself. So this is the general operation. In detail, you can see here the scanning device. So my colleague Raimund Edlinger is scanning this structure. You see it's not very high, maybe 1.5 2 meters high, but he has to go to the wall to scan all the niches and In this case, we also have some marker to have a secure element, considering of one measurement to the other measurement. But in general, it was not necessary done all the time. So this is the scanning device. To be more precise, at first we took a Lenovo Fab Pro, which has been constructed 2017, but Lenovo cancelled the production. Nowadays we took an iPhone 15 Pro Max, which concludes of a depth sensor, of a camera, and also of a gyroscope. And by this we have been able then to follow this RT map algorithm, which is the real-time appearance-based mapping, which is a product also of the Google project. So it also has been part of the project Tango, which has been implemented also 2017. Additionally, we had to apply some diffuse illumination in front of it. So this is then the result. On the left side you see the results of the mono camera, and on the right side you see some result of the LiDAR sensor. So these are then measured 3D point clouds and meshes of the structures inside the cave. So you will find out there are some difference. Here at the iPhone we have a lot more structural elements as we get in the LiDAR sensor. So this is some of an advantage also from the iPhone, that we get a little bit more details of the structure itself. Finally, we then produce a 3D model of this Erdstall, and this is the 3D model. And the next screen you will see some video, which is a 3D mesh of all of the points of the 7 chambers connected to each other. So we had 7 measurements, and then they have been connected within the slopes. But you have the possibility now to get into the caves and have some imagination what is happening inside the cave. So this is one of our first results. Now I will highlight some other examples of results of our measurement we have been found out. The first one, we have found out that there may be some doors inside the cave, because we have seen the structure of the frame of the door inside the cave. So this leads us then, in combination to archaeologists, to the idea this is some place for a wooden door, and the wooden door has been fixed by the 2 plots on this side to have a defense meaning. So one who is inside the cave is able to hide from outside comings because they cannot get into it. Secondly, they are pressed with sticks, and they then have to be told, please keep outside, but we can be able to do something with you. Then we have another finding without the measurement, without the metrology, which is in this case the central building shaft. It is very essential for us to find this, because we got then the idea how did they dig the caves. At first they dig the building shaft, which is 1 meter in diameter, 6 meters in depth, and from this building shaft the chambers have been built from this side, from this side, from this side, and so on and so on. So it was easy to do all the material out of the building shaft and to put the material away. After this, finally, then the slippages have been digged in the hole, and finally the building shaft has been closed and has been spilled by material to get this Erdstall to the primary purpose. The primary purpose is to hide people. And if there is no building shaft, you can have the enter here to the Erdstall, but you have to climb two other one slips to get into the last chamber. So it's just possible for one person at the same time to get into it. And it is easily to defend the hiding people there. Because of the door is at this place, and we have another feature which is a stone which is lying in front of a slip edge. You see the slip edge is a diameter of 40 centimeters. So every time you go to the chamber, you have to climb to this slip, either up or down. For me, it's funny. I've been done this several times, but I know of other people who cannot imagine to do this. So you don't have to be claustrophobic. But it is possible to get there, and for this stone, it is available to close the slip and to stand on the stone, so nobody can have the access from downstairs. Secondly, we don't know exactly, but we found out from the measurement there are signs in the wall. Maybe this is a sign of the architect or of the building people, but the aim of the signs is not very clear nowadays. Then, because of the illumination, all of the cave is dark. There are some special niches here where oil lamps have been placed on the wall, and the oil lamps then illuminated all of the scenery. And we also can find this. You can see this is a part of the 3D model. We had a 3D print out of the model, and also on these ones you can find the erection of these niches. Yeah. What are then the next steps of operation? We want to evaluate the accuracy and the reliability of our mobile measurement system with respect to LiDAR sensors. So we know the LiDAR sensors are very accurate, reliable, but we want to know how reliable and accurate is our system. Then we want to develop a MOBIS, which is a mobile Erdstall scanner system, and we want to measure other Erdstalls also. So we know in Europe, from France to Bavaria to Upper Austria, Lower Austria to Czech Republic, there are 300 to 500 Erdstalls, and we want to measure some of them, and after this to do a typology, to have some Erdstalls of the same architecture, and then maybe we find out there are people who are wandering from one Erdstall to the other one to build this. So this project is funded also by the Austrian government, by the Bundesministerium of Kunst, Öffentlichkeitsarbeit und Sport, and also from the Upper Austrian government. It's a project of making it reliable and visible to other people. So every time you climb into the Erdstall, you destroy something of the Erdstall. So we also want to reduce the number of entries, but we want to make it public and have a lot of people decide what is then the meaning of an Erdstall. And therefore we have the 3D model, and on this homepage we will also then have the possibility to show this to the viewer, that they can virtually go into the Erdstall. And if you want to follow me on the YouTube channel, there is one video. I climb from the very beginning to the last chamber and going back again. It's very impressive, and I want to support some feeling of being there without having you also to be there. So this is one of the main ideas from us to deliver the sense and some feeling of this Erdstall. So there are a lot of different aspects archaeologically to support the science of archaeology, but also for the public to get the knowledge about this. So This is my presentation. Thank you for the audience. I would be happy to answer if there is any question.